In this video, we'll be showing how to find the hydrogen and hydroxide ion concentrations of strong bases. Now let's focus on basic solutions. Basic solutions are solutions that have more hydroxide than hydrogen ion. Like acids, we have both strong bases and weak bases. The strong bases are things that are completely dissociated, 100% dissociated in water. Notice that I said dissociated, not ionized. In the case of an acid, it has to be ionized. It is molecular and it turns into ions. In the case of a base, it is already ionic, so we don't have to do that. All we have to do is break the ions apart, which we call dissociation. So there are 8 strong bases that we'll be discussing, and they are basically the group 1A bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, and part of the group 2A ones. And these are the ones that are soluble. So this is exactly what we did before. We learned about the solubility of bases, and these are the ones that are soluble bases. So then we have calcium hydroxide, strontium hydroxide, and barium hydroxide. The only one that you may recall as soluble but not listed on here is the ammonium hydroxide, and we're going to talk about that one separately. Okay, so let's do a couple calculations with these. I'm going to model this like we did before, where I'm going to say, what if I have 100 particles, rather than giving you the exact answer first. So if we're going to start with this, if I had 100 particles of sodium hydroxide initially, and we put that in water, initially we would have no sodium in the water, but we would still have 10 to the negative 7 molar hydroxide, because recall in pure water, there is some hydroxide and hydrogen. They are equal to each other, and it's 10 to the negative 7. So we're going to start with that amount. After the reaction, because this is 100% ionized, it's already separate. There's 0 NaOH, and now we're going to have 100 particles of Na plus and 100 particles of OH minus, plus 10 to the negative 7. Now because 10 to the negative 7 is so small, we're going to ignore it in the calculations. So next, we're going to look at this again, and we're going to now try it with the numbers that we have here. And so here it's asking us if I have 0.1 molar NaOH, and I place that in pure water. Initially, we have 0.1 molar NaOH. Initially, we'll have 0 molar Na, and we'll have 10 to the negative 7 molar of hydroxide. After the reaction, we'll see that all of it is separated, so there's no NaOH left. It's completely separated into its 2 ions. And we'll find that there is 0.1 molar sodium and 0.1 molar hydroxide ion. And why did I come with 0.1? That's because that's what we started with. So we have 0.1 to start with. It completely separates into the 2 ions, dissociates into the 2 ions, and we end up with 0.1 molar for each ion. So we can easily find the theoretical hydroxide ion concentration for a basic solution. And in this case, it's whatever I start with. If it's a strong base, whatever I start with is how much hydroxide I'll have after the dissociation. So here we had 0.1 to start with. We're going to have 0.1 to end with. And I'm going to rewrite that into exponential form, and that is 10 to the negative 1. So that's our theoretical hydroxide concentration. Now recall that in water, hydrogen concentration times hydroxide concentration is going to be 10 to the negative 14, as long as we're in water. So we can rearrange that equation to say that the hydrogen ion concentration is equal to 10 to the negative 14 divided by the hydroxide ion concentration. So in our case, we're going to see that then the theoretical hydrogen ion concentration will be equal to 10 to the negative 14 divided by 10 to the negative 1, which is 10 to the negative 13. And now it's your turn to try this. What is the hydrogen ion concentration of a 0.001 molar KOH solution? Pause the video while you try this. The first step you should do in a problem like this is to identify whether you have an acid or a base. So the first thing we see is that we have KOH, which of course is a base. The second step is to identify whether it's a strong base or a weak base. And because it's potassium ion, that tells us this is a strong base. So we're seeing the hydroxide says it's a base. The potassium tells us that this is a strong base. Next, we're going to look at the concentration, and we see that it is 0.001 molar, and we're going to change that into exponential form, so that will be 10 to the negative 3. Now, before the reaction begins, the first thing we know is that as we place the KOH into the water, it is going to dissociate, but initially we have only KOH present, and the amount we have is 10 to the negative 3 molar. This is going to break into those ions, but initially there's no potassium ions, and in the case of hydroxide, there is some hydroxide because we're placing it in pure water, and so its concentration is 10 to the negative 7 molar. Now, after the dissociation, because this is a strong base, it dissociates 100%. That means there is 0 KOH left over, and we have all potassium ions and hydroxide ions in the solution. So the potassium will be the same number we started with, which is 10 to the negative 3 molar, and the hydroxide will be 10 to the negative 3 plus 10 to the negative 7, but we're going to round that off to just 10 to the negative 3 because the 10 to the negative 7 is so small. Okay, so now we have our concentrations of potassium and hydroxide in the solution. So let's find out what our theoretical hydroxide ion concentration is. We just figured out that it should be 10 to the negative 3 molar. That's what we expect it to be if we have this concentration of KOH. What is the theoretical hydrogen ion concentration? That's going to be related to the fact that we're in water, so we're going to use that equation that we've used before that says that the hydrogen ion concentration times the hydroxide ion concentration is equal to 10 to the negative 14. Rearranging that equation, we see that the hydrogen ion concentration is equal to 10 to the negative 14 divided by the hydroxide ion concentration that we have in our solution. In that case, the theoretical hydrogen ion concentration then is 10 to the negative 14 divided by 10 to the negative 3, which we get from our calculation, which is 10 to the negative 11 molar. Let's try one more. So in this case, we're going to ask what is the hydrogen ion concentration of a 0.00001 molar KOH solution. That's 4 zeros in front of the 1. And go ahead and stop the video and come back when you've tried it. Again, the first step is to identify this as an acid or a base or a neutral. Because it's a base, we know that we're only going to be able to find the hydroxide ion concentration directly. We're going to have to do a calculation to find the hydrogen ion concentration. So we know it's a base. The next step is to identify it as a strong base, and because it starts with potassium, this is one of the strong bases that you've memorized. We see that that number that we see has 4 zeros and then a 1. We're going to write that as 10 to the negative 5 in its exponential form. That is our initial concentration of KOH, so we put 10 to the negative 5 there. Initially, we have no potassium ions, but we do still have hydroxide, which is 10 to the negative 7 molar. After the dissociation, we see that the KOH has become 0. Again, it's 100% dissociated, so there's no KOH left. It is completely turned into the ions. So we now have 10 to the negative 5 molar potassium and 10 to the negative 5 plus 10 to the negative 7 molar hydroxide. We're going to ignore, again, the 10 to the negative 7 that we added because it is very small. That's like adding $1 to a $500 sample. So we're going to ignore it and just say it's $500, or in this case, 10 to the negative 5 molar. So that tells us our theoretical hydroxide concentration is 1 times 10 to the negative 5 molar in hydroxide. Then, after rearranging our equation of hydrogen times hydroxide is 10 to the negative 14, we find that the theoretical hydrogen ion concentration is 10 to the negative 14 divided by the hydroxide ion concentration, which in our case is 10 to the negative 14, divided by 10 to the negative 5, or 10 to the negative 9 molar in hydrogen ion. And this is our last one. We're going to have you look at what is the hydrogen ion concentration of a 0.01 molar KOH solution. Pause the video while you try it. So the first step, identify this as an acid, a base, or a neutral. We see that it ends with OH, so we know that this is a base. Starts with a metal. The metal is potassium. It is a group 1. Tells us it's a strong base. And then we look at the number that we have, and we have 0.01 molar, which can be written in exponential form as 10 to the negative 2 molar. Our initial KOH concentration then is going to be 10 to the negative 2. Our initial potassium ion concentration is 0. Our initial hydroxide ion concentration is 10 to the negative 7. Our final KOH concentration is going to be 0 because it is 100% dissociated. Our final potassium ion concentration is 10 to the negative 2 molar, and our final hydroxide ion concentration is 10 to the negative 2 plus 10 to the negative 7. We're going to ignore the 10 to the negative 7, so we're going to estimate it as 10 to the negative 2 molar. That means our theoretical hydroxide ion concentration is 10 to the negative 2 molar. Our theoretical hydrogen ion concentration, after we've rearranged the equation of hydrogen times hydroxide, is 10 to the negative 14. When we rearrange it, we see that the hydrogen ion concentration is going to be 10 to the negative 14 divided by the hydroxide ion concentration, which in our case is equal to 10 to the negative 14 divided by 10 to the negative 2, which is equal to 10 to the negative 12 molar. And that is our hydrogen ion concentration.